other vehicle. And MaTeLo, the aim is to design in MaTeLo the different possibilities of behavior and then generate the test cases in order to be run into scanner. So how it works? You can have some requirements. These requirements can be from any kind of tool like HPLM Quality Center, TestLink, Squash, Doors, some Word, and then you need to build some scenarios. If you start with this methodology, in order to avoid you to start with an empty screen, we provide you a library that can help you to build your library of scenarios. Like, for example, zip in, zip out, I will explain it after, merge, and you have, and you can do your model by yourself. These models are composed with states and transitions and conditions, and it is based on Markov chain. And this model will draw in this model all the environments you can have. And then you can select the coverage, what you want. So you can have a sort of a kind of button which selects the amount of combinatorics and the number of trees of test coverage you want to have, and the number of tests you can have. And then you press an offline button, and this offline button will create automatically some test cases, merge in test suites, all the steps, all the input and all the outputs, the expected results, called a test oracle. This test can be, if you want, exported to any ELM tool, like, for example, HPLM Quality Center, Silk Central, Squash, TestLink, or other ELM. And also, you can, after, generate automatically any kind of script. So, in this case, it is what we call offline methodology, because we generate test cases, and then we transform these test cases in script. This script, in this example, can be a script able to be run directly into the 3D tool, like, for example, a scanner, but it can be also other tool like IPG, car maker, or Prescan from a Siemens company. So the format of the tool can be some raw XML, any XML file, any custom script. And then this script is run in the 3D tool, and the autonomous vehicle, you do a test harness with his captor, and the autonomous vehicle think he is in his environment with all his captors stubbed into this loop. So this is the offline mode. We also have an online mode, and this online mode, the aim is during the test case generation, at each test case, at each test step, we get some data, some parameters from the environment, and then depending the state of the simulation, we can manage and we can create specific test case automatically during the test case generation. And like that, we can, for example, create test case one after one, and each test case starts with the initialization of the end of the previous test. And then we can, for example, do a lot of tests in a whole road, and the test adapts during the test generations. One word about the model. So in order to do that, you need to build your own model. So we have some kind of families. For example, the weather. We're going to create a weather design. Road will be all the possibilities of the kind of road, the rules, the vehicles, the scenarios, the cutting, cutout, the system you can have to design the system you have in a car if you brake, if you do not have any oil in your car, and all the events you can have. And we split this model in families, and each families after is through one by one to find one combinatoric. So it uses some probabilities into its. In each model, you have some probabilities to go to a state to another, and also we have some condition in order to say if you go first, for example, in a family of the weather and you select snow, for example, after you can only use some parameters depending the snow. So all the parameters are linked together and the families are built to work together. So all the test case generated can be executed in real life. So with this behavior of test case, we use, for example, the Monte Carlo speed convergence first, but the issue is we are going to have a lot of doubles. Each time we create a new test case, we have a chance to be the same as before. So if we generate millions of test cases, you will have this kind of curve. So it will be more and more slow to reach all the distribution of the model. So I will explain you how we can avoid that after. So here it is a kind of model where we see, for example, the road. In this model, all the equivalence classes are designed with a state. So, for example, here we have the number of lanes, the downhill, the slopes, and in the first, the top here, all the equivalence classes are not dependent. There is no dependencies into these equivalence classes, but in the bottom part, you have dependencies in two classes. For example, here, if you have right turn, you will have a radius positive, but in left turn, radius are negative. And then the speed limit is depending the radius. So you can link the equivalence class together. For the scenarios we build, for each kind of scenarios, for example, cut-in, zip-in, for example, this car is going to come on this road, zip out, this car is going to exit the road, or cut-in, this van is going to be in front of the vehicle autonomous, cut out. After we can have also a pedestrian or obstacle, and for each kind of scenarios, we are going to build a specific model in order to create this behavior. And for each scenarios, we can launch these scenarios depending what we have as parameters. For example, if we have only 2, 3, or 4 lanes, we can do basic scene or cut-out scene. But if we have only 1 lane, we can only do some basic scene. So here it is a cut-in model, for example. So we split all the environments into equivalence classes. For example, autonomous vehicle here in green, he has no cut-in zone here, a collision zone here, a near cut-in zone, and a secure cut-in zone. And here it is a cut-in vehicle, and all the parameters are managed by MaTeLo, and all the parameters are chosen by MaTeLo in order to create the behavior what we expect. So some parameters are random into equivalence classes, and other parameters can be calculated and depend of what we choose before. For example, the mean and max of each variables can be calculated depending the previous data. So each time, if we create a cut-in, the cut-in will be created by MaTeLo, and there is no no error possible, you're sure to have a cut-in. Okay, now, what is the issue? The issue is we have, if you want to have a lot of test cases, for example, few millions test cases, because we can generate this kind of amount, you will have some doubles. So it is not easy to converge to the distribution of the system. So we use a method, name Gibbs. This method, Gibbs sampler. This method is used in order to reduce the number of test cases in order to converge quickly to the distribution of the system and to have the lower number of test cases to reach the distribution faster. So you can imagine that all the scenarios, all the families are in a kind of road, and you can do loop on a road, and for example, you have some sectors. So here it is the sectors of events, the sectors of scenarios, the system and road, and you give a weight to each sector. And the aim of Gibbs is when you do a term, you have more luck to choose one sector. For example, here he chose road, and then he only changed the combinatorics of the road. He's not going to choose the other combinatoric, and he will reuse the previous combinatoric on other families. We do the same. For example, here he chooses the scenario, and he only chooses scenario, and he keeps the other data. One more time. Here he chooses scenario, and he chooses only another scenario, and keeps the other vehicle, the other combinatorics. And like that, if we do a comparison with the Monte Carlo approach, here it is Monte Carlo approach and Gibbs approach, we see that the Monte Carlo is much more faster to the distribution of the system. The stationary distribution is the sample of your test case that represents the probability you set in your model. And you go very much faster. You go very much faster to this stationary distribution. So how we can do that into MaTeLo? In fact, we take all the family and we use it in a parallel model like that, and we set a weight in each transition of the model. The weight is the importance you want to set on a family, not an equivalence class, but on a family. So if you want to have more combinatorics only on scenario, you will have an arrow, more probability here, and you have more chance to have combinatorics on scenario than on rules. For example, if it is less important, you have less probability to choose it. And then you can either regenerate at each test case and reuse previous data of other unused combinatorics, or you can have a loop in order to change, to go, for example, in the scenario, to pick up a scenario, then you generate your script scanner, for example, and after you do another combinatorics. And each time you use all data in other family, even if you don't change it at each loop. And here we do some, you have here in red the Gibbs sampler speed to the convergence of the system, and it is a geometrical speed, and if you use the Monte Carlo, the random approach, it is much more slower when you go to a high number of test cases. The number of test cases, it is when you have more than 500,000 or 1 million test cases. It's a big number. At the beginning, it's the same speed. Okay. And then here it is okay, so for example, okay, and here it is a demonstration of what we can have at the end, but it doesn't start. It should, but normally you see the model which is animated during the test case execution, and during the test case execution in the online mode, you can see your test and the test execution with different kind of view, and MaTeLo change it and adapt the test during the execution. Okay, and this was a moment finished.